All right, guys, welcome to a video lesson. I wanted to address the solubility chart. It's called the solubility chart. You guys will see it in the materials section on your in your Google Classroom. This is what you guys are seeing. Hopefully it's big enough. Let me make sure. Yeah, so hopefully you guys can see. So I'll remind you guys, remember when you were dealing with ionic compounds, an ionic compound is a compound that exists between usually a metal and a nonmetal, or a metal and polyatomic ion. And you remember the metals tend to be cations, which means they've lost electrons, and then the nonmetal or the polyatomic ion is negative, indicating it gained electrons. And so it's the positive and negative electrostatic attraction that holds those together. Well, some substances, some ionic compounds are what you'd say soluble in water. That means when you put it in water, it's going to dissolve. You guys know a common one. What's a common ionic compound that's soluble in water? You got it, salt, sodium chloride. This shows us what types of compounds we can expect to be soluble and which are insoluble. And you'll notice by the solubility chart, it indicates a list by the anions. So these anions would be bound to a cation in an ionic compound, and it tells us whether or not it's soluble or not. So you can see right up here, first of all, common anions like nitrate, acetate, chloride, bromide, iodide, and sulfate, these all tend to be soluble. So when you have a metal attached to these, when you put it in water, you would expect it to be able to dissolve. However, there are a few exceptions. For example, all nitrates, if it says none, there's no exceptions, that means all nitrates are soluble. All acetates are soluble, but you can see there are a few exceptions. When it comes to these halogens, you remember the halogens here, remind you guys, remember you have your periodic table. I would bring up your periodic table, and I remember these are your noble gases, and then these are your halogens. You'll notice it's that with a lot of these halogens, chlorine, bromine, iodine, which are in here, they are typically soluble except if they are bound to silver ions, mercury ions, or lead ions. You can see these are common exceptions. And so it just helps. You guys will have this available, but it kind of helps if you know some general trends. If you're just like, oh, most nitrates are soluble, most halides are soluble, with the exception of these ones with silver, mercury, and lead. Now, in general, these anions tend to be insoluble. So when you have an ionic compound with these anions, they tend to be insoluble. The sulfides, the carbonates, that makes up a lot of the rocks. You'll find a lot of, calcium carbonate would be limestone. Phosphates tend to be insoluble, and also hydroxides. However, they have some exceptions. Notice the exceptions. Notice an exception for all of these. When any of these are with alkali metals, I'll remind you guys, the alkali metals are here. It's that first group: sodium, lithium, sodium, potassium. These are the alkali. So anytime you have an alkali metal in a compound, you can expect that compound to be soluble, and you can see that's the case. And also if it's the ammonium cation. And then also, you can see a few exceptions are calcium, strontium, and barium. Those are the alkaline earth, and those are the heavier ones. So those are the ones like right down here. So basically any substance with these metals in it will tend to be soluble, as those are exceptions to the anions that are insoluble. You guys, we're going to practice. I know that could be a little confusing, but I want to see if you guys can apply the solubility chart. So I'm going to ask you guys to make a prediction. Okay, so what I have here is sodium carbonate. Sodium carbonate. I will write that down. Sodium carbonate. The question I have for you is, do you expect sodium carbonate to be soluble in water? When I place this in the water, will it dissolve, or will it stay as a solid? And you guys, the reason why it dissolves, I'm just going to remind you, I'm kind of jumping ahead here, but it all has to do with the properties of water. I'll remind you guys, remember, water is polar. For those of you guys who haven't had chemistry in a while, this is going to be new. You remember, because of this highly electronegative atom, oxygen, that pulls the electrons, so there's an uneven distribution of electrons. So water molecules will have a partial negative side and a partial positive side. When an ionic compound is soluble, what that means is for example, you guys know what's a common soluble salt? And in fact, salt is the generic term we use for ionic compounds, and that's the one that we use for our common table salt. Is salt, NaCl. So why does salt dissolve in water? Because what happens is the positive sodium ions are attracted to the negative side of the polar water molecule, and the negative chloride ions are attracted to the positive. So in this case, the sodium ions have a stronger attraction for the negative side of the water molecule, and the negative anions have a stronger attraction for the positive side of the water molecule. That attraction is greater than the attraction that these have for each other. If the cation and the anion had a stronger attraction for each other than they do for water molecules, what's going to happen when you put it in water? It's just going to stay as a solid, because the anion and cation have a stronger bond attraction than they would have for the water molecule. Okay, so you guys are going to make a prediction once again. Sodium carbonate, what you want to use is use your solubility chart. See if you guys can read the solubility chart correctly. And if you guys need more time, I'm going to do it right now. If you need more time, pause it. Okay, so now I'm going to add it. And here I have a spatula. You guys know this is a typical device we use, equipment we use to transfer solids. I'm just going to put it in water. Okay, so I put it in water. And you know what? In actuality, guys, it's not to say that this is completely soluble and these are completely insoluble. There's always varying degrees. To some measure, everything will dissolve slightly, but for the most part, when we say soluble, we're saying it will dissolve to a great degree, and when we say insoluble, very minimal will dissolve. Okay, so we're going to look at this, and you guys had a prediction. You said yes, it's soluble, or no, it is insoluble. And I want you guys to see. If we look, you guys see any solids in there? And if I stirred it a little bit more, it'd probably even work better. But you guys should see it fully dissolved. Sodium carbonate is indeed soluble, and we should have guessed that. And right off the bat, why should we have guessed that, guys? Right off the bat. Somebody might have said, "Oh, well, I thought it was insoluble carbonate." But you guys, what was carbonate with? It was with sodium. And what's sodium? Sodium is an alkali metal. Remember, any ionic compound with an alkali metal is always, always, always soluble, and I put that note at the bottom. Okay, let's try another one. See if you guys are on top of things. Here I have calcium phosphate. Calcium phosphate, I'll write that down. Oh, and then just a little, you guys are going to have to do this. You guys have to make a proper formula, and if you guys understand valences, and I believe you've already looked at that, you can also look at the valence sheet on your material list. Calcium has a valence of +2, phosphate has a valence of -3, and if you guys remember, to get the proper ratio, we look at the valences and the sum needs to equal 0. So the question is, so I have, this is a +2, this is a -3, how many calcium ions are bound to how many phosphate polyatomic ions? Well, what you can do is you can get the least common multiple of 2 and 3, which is 6. So the question is, how many positive 2's will go into 6? 3. And how many -3's will go into -6? 2. So I put a parentheses here, 2. So the purpose of memorizing valences is it helps you to predict the ratio in which atoms will combine. So anyways, that is the formula, calcium phosphate. Look at the solubility chart, predict whether or not you think calcium phosphate is soluble or insoluble. Okay, you guys can always pause it. Okay, so here I have my calcium phosphate. I'm going to use my spatula. And I'll try to add equal amounts, so we're comparing the same, right? If we're going to compare, we want to, so that's about as much sodium carbonate as I added. So I'm going to put this in the water. Okay. And I'm going to stir it to the same measure that I did the other, right? What we want to do is increase random molecular motion, allow the ions to interact with the water molecules, and if they have a greater attraction for the water molecules, it's going to dissolve. If they have a greater attraction for each other, they're just going to remain a solid. So I'm doing this, shaking it as much as I can, and you guys look, and I don't know if you guys notice, if you guys can see at the bottom there. Oh, you know what? I'm sorry, guys. I'm putting it in front of the projector, and you guys are like, what the heck is he doing? Oh, man. Hopefully you guys saw that. My bad. Whew, I got to get better at this, guys. I should be putting it in front of the camera. Whoa. But anyways, you guys see this. Oh, anyway, so going back, because maybe you didn't see it. Here was the sodium carbonate, sorry guys. And you guys should see it is fully dissolved. My bad, whoa. And then here is the calcium phosphate. And I don't know if you guys can see, but there's chunks of calcium phosphate in the bottom. It's relatively insoluble. And we should have predicted that, right? Phosphates. Because indeed, most phosphates are insoluble, but we have to check exceptions. This was calcium phosphate. Is calcium an exception to the fact that most phosphates are insoluble? No. The only exceptions are if it was with ammonium or, once again, the alkali metals. So that's how you use your solubility chart. We want to finish with one last thing. I want you guys to make a prediction, okay? So here I have two solutions, okay? Two solutions. One is lead nitrate. In fact, I didn't even write that correctly. This is lead nitrate. And you guys will get better at that when you guys know how to use your valence sheet and get used to it. Lead has a +2 valence, nitrate has a -1, and therefore there's 2 nitrates for every 1 lead, okay? And then there's potassium chloride, okay? So the question is, when I put these together, will there be a precipitate that forms? And what we're saying here is, here's how it works, guys. Okay? So obviously, if these are in solution, that obviously means lead nitrate is soluble and potassium chloride is soluble. And you guys should be able to confirm that with the solubility chart. That would indicate both these are soluble. That's why you can see solutions here, right? Okay, and they're both, how would you guys describe them? 2 clear solutions, okay. So when you put in water, here's what's happening. Once again, why do they dissolve? Because what's happening is the ions are separating, the positive and negative ions. So what this is separating into is lead ions, positive ions, and also nitrate ions. You have these positive and negative ions, which normally would be together. And why do they dissolve? Because these have a greater attraction for the polar water molecules than they do for each other. And likewise this as well. This will separate into, so what you have, so just so we're clear, you guys can't see it, but you know what? There's lead and nitrate ions floating around in here, and there's potassium and chloride ions floating around there amongst the water, right? These are being stabilized by the polar water molecules. Question is, when I put those together, will a precipitate form? A precipitate's a fancy word for a solid. Well, you got to be able to use your solubility chart. So how you guys figure this out is you guys got to think, what kind of combinations could possibly form such that one might be insoluble? You guys remember this? Think about it. So if I put them together, all these ions will be together, right? So what will the positive ions have an attraction for? Will they have an attraction for each other? No. Like charges repel. What will positive ions have attraction for? Negative ions. So what you want to look at is, so obviously the attraction between the positive potassium and the negative chlorine is not as strong as the attraction that they have for water molecules, but you have to consider, perhaps does potassium ion have a much stronger attraction for the negative nitrate ion, or does the positive lead ions have a stronger attraction for the negative chloride ions? So think about that. So my question once again is, do you think a precipitate will form when I put those together? Okay, so you guys can pause if you want. Okay, so let's look at this. So now I'm going to just add these two together. And that did not happen. You know, it should be a lot more dramatic. Kind of seeing it. I was hoping it was going to be a lot more dramatic, but if you guys look, hopefully you guys can tell, it looks a lot blurrier. You guys are seeing, I would imagine, a precipitate forming in there. It looks kind of like snow coming down, and if I leave it and you guys can see the bottom of it, okay? So we should have predicted a precipitate would form. And what is the precipitate that forms? You guys think about it. What do you guys think this white precipitate at the bottom is? Well, let's think about it. Let's think about the possibilities. What if these came together? Potassium and nitrate. Would that form an insoluble compound? The answer is no, because you guys remember all nitrates are soluble. And what else do you guys know? All alkali metals, remember this is on that first column, an alkali metal, those are always soluble. So guys, that's not going to have a strong attraction. Well, now let's think about this. Let's look, could this possibly combine. Lead ions with chloride ions. So I look at chlorides. Chlorides are normally soluble. However, what's a notable exception? If it's bound to a lead ion. So, you guys, what's happening is the lead ions are combining with the chloride ions and forming what? You guessed it, lead chloride. And that's what we see. All right, guys, so that should help prepare you guys for, I don't know what happened there. That should help prepare you guys for the corresponding AP. You're gonna have an AP type test question pertaining to this material. All right, guys, we'll see you.